Welcome everyone. Today we're going to extend the multiplication table that we started discussing last time from the 5 by 5 case to the 10 by 10 case. It's a big step up, and it's a major achievement for young people, usually around grade 3 or something like that, to get this 10 by 10 multiplication table under their belt. So we're going to talk about perhaps how we might help young people in achieving this goal, and maybe some orientation about how we should think about presenting this very important aspect of arithmetic. Let's start by reminding ourselves about the 5 by 5 multiplication table. And I think it's very useful for young people to first start with this case, to master the 5 by 5 multiplication table first. You could easily spend a year, like perhaps in grade 2, solidifying this table, making sure they understand what the entries mean, and are very, very quick in being able to come up with the answers. So here we have the table here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The entries tell us, for example, what 5 times 3 is. We go along this row and down this column. That entry there is the 15, telling us that 5 times 3 is 15. And hopefully all your students or young children will know what this means pictorially or geometrically. What we're doing is we're counting the number of squares or little cells in a rectangle. A rectangle which is 5 in this direction and 3 in this direction. In other words, it's a 5 by 3 rectangle. And we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 little cells in this 5 by 3 rectangle. So we say that 5 times 3 is 15. In this case, 5 rows, 3 columns. And we can think about 5 times 3 as being 3 plus 3 plus 3 plus 3 plus 3. In other words, 5 copies of 3. And here's that whole multiplication table telling us what all the possible multiplications between two numbers in the range 1 to 5 are. So today we want to extend this. We want to go beyond this to the 10 by 10 table. So this is grade 2 mathematics. We're now going to go to grade 3 mathematics. And it's a very big step that takes a lot of effort and determination for a young person to master. But it's very, very important stepping stone to mathematics. A very important tool that young people have to master. All right, so here is the table. Here's the whole table all at once. 1 to 10, 1 to 10. And the entries here tell us what all the possible products are between numbers in the range 1 to 10. Now I've put this whole table up in front of us here so we can see it all at once, but it's probably reasonable that students are presented with this a little bit at a time, and that they build up to understanding this entire table. But let's at least put it up there and have a look at it, because at some point the student really does want to see the whole table in front of them. So they may have learnt the table one row at a time, and we'll talk about that in a little while, but at some point they should be able to see the whole table in front of them, and probably they should be able to write down this whole table. That's an important skill that a student should be able to do at some point. So let's talk about it. First of all, I've made the division between the numbers from 1 to 5 and the numbers bigger. So in this block up here, we see the table that we've already talked about, the 1 to 5 table here. So we've just copied that table right there. So 5 times 3 is 15, just as it was previously. So we're extending what we already know with these 3 new aspects. And there's a symmetry involved that makes things a little bit easier. And the basic symmetry is that 5 times 3, this 15 here, is the same thing as 3 times 5, that 15 there. This is the basic commutative property of multiplication. And what that means is anywhere in the table, if you have A times B, the entry should be the same as the entry under B times A. So for example, here we see 7 times 8. We see that 7 times 8 happens to be 56. And if we looked at 8 times 7, well, we would also see a 56. Another example, 4 times 9. There's the 4 times 9. That's 36. While 9 times 4 is also 36. All right, so let's go over it. Let's have a very careful look at this multiplication table. We want to become very familiar with it. All the numbers are important. We need to understand all the numbers on this table. So maybe we should start by reading it. All right, so let's read the table. And that's not a bad thing to do. It's not a bad thing for young people to do, because the oral recitation of the entries helps us in memorizing the values. So we want to understand what the entries mean, but we also want to rote memorize them so that we don't have to think too hard about what 4 times 9 is. We know that it's 36 without having to compute. Of course, as the student is learning this, they will often have to compute, have to figure it out. Well, you know, there'll be different kinds of strategies, we'll talk about that, about how to compute 4 times 9 if you've forgotten. So let's go over the table rather briefly. We'll do that by looking at various rows. So the first row is the simplest. Multiplying by 1 is very simple. 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, 1 times 5 is 5, and so on, up to 1 times 10 is 10. The second row is multiplying by 2, which generates the even numbers. Those are the multiples of 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Those are the entries that we get when we multiply the numbers 1, 2, 3, 4, 5, and so on by 2. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. That should be familiar from the 5 by 5 table. And now the new thing, 2 times 6 is 12, 2 times 7 is 14, 2 times 8 is 16, 2 times 9 is 18, and 2 times 10 is 20. Each time we're going up by 2 from the previous one. So if we knew what 2 times 5 was, if we knew that was 10, and we had to calculate what 2 times 6 was, we could just add 2. Go from 10 to 12 by adding 2. We're adding 2 every time we go along this row, starting with 2. Another observation is that the ones entries, which are 2, 4, 6, 8, and 0 here, are repeated in the second part. 2, 4, 6, 8, and 0 again. So the only difference between this half and the first half is that now we have 1 10 in front of all the digits, with the exception of the 10 turning into a 20. The multiples of 3 along here. When we multiply by 3, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, and then the new ones, 3 times 6 is 18, 3 times 7 is 21, 3 times 8 is 24, 3 times 9 is 27, and 3 times 10 is 30. All right, I'm not going to go through all of them. We'll just have a quick look. Here are the multiples of 4, which are a lot like and closely related to the multiples of 2. They're all even numbers. In fact, they're all every second even number in this row here. So 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, and so on. Again, there's a kind of a repetition of the ones. 4, 8, 2, 6, 0, 4, 8, 2, 6, 0. Multiples of 5 are perhaps even easier. The ones just alternate from 5 and 0. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. But it's a little bit different from just being able to spout the multiples, we need to be able to know that this 35 is actually 5 times 7, while the 45 is 5 times 9, and so on. There's the multiples of 6, from 6 to 60, going up by 6 each time. And then the multiples of 7, which for many students are the hardest to remember. 7's a little bit less regular than the other numbers, because it's a prime. Multiples of 8, which are a little bit like the multiples of 4 or 2. They're all even numbers. 8, 16, 24, 32, 40, and then that pattern of 1s repeats here as well. The multiples of 9, there's a pleasant pattern to that we'll talk about a little bit later. And perhaps the simplest ones after multiples of 1 are the multiples of 10, just obtained by adding a 0 to all these numbers here. So 10 times 1 is 10, 10 times 2 is 20, just add a 0, 10 times 3 is 30, 10 times 4 is 40, always just add a 0, that's how we multiply by 10. Okay, so a lot of work. Takes many months for a young person to master this table. And if you're an adult and you have never learnt this table and you want to get better at mathematics, this is a really good place to start. Just sit down one Sunday afternoon with a couple of cups of coffee and say, I'm going to learn this table. I'm going to learn it really, really well. I'm going to memorize it. I understand what the entries are. I'm going to memorize that 8 times 7 is 56. That 9 times 3 is 27. That 6 times 8 is 48. And so on. The rectangle property, that was a nice property we mentioned in the 5 by 5 case, that's still valid here in this bigger table. And what is it? Well, it's the property that a particular entry, say this 56 here, is actually counting something that you can see in the table. So this 56 represents 7 times 8. And 7 times 8 is the number of cells in a rectangle, which has 7 and 8 as its dimensions. Well, in this table there already is exactly such a rectangle. And it's exactly the rectangle whose bottom corner is this 56, and whose top corner is this one. So the rectangle that you get by going all the way over here and down here, so the one whose corners are 1 and 56, that rectangle has 1, 2, 3, 4, 5, 6, 7 rows, and 1, 2, 3, 4, 5, 6, 7, 8 columns. So that's a 7 by 8 rectangle. And that 56 then is actually counting the number of cells in this rectangle. That's another way of thinking about what this 56 actually means. It's actually referring to something in the table itself. A little bit simpler to see for a smaller number. For example, this 6 here represents the number of cells in this little rectangle with corner 6. 1, 2, 3, 4, 5, 6. This 14 represents the number of cells in this rectangle here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. The other feature of note that I've emphasized here are the diagonal elements. They are particularly important in mathematics. They are the squares. The numbers that you get when you multiply a number by itself. So 3 times 3 is 9. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. And 10 times 10 is 100. It's especially important that students remember well the diagonal entries of this table. Those are the squares. All right, so let's talk a little bit about strategies for learning this table. Or if you're helping a young person develop mathematics, strategies for getting them to learn the multiplication table. So my first suggestion is to start with the 5 by 5 table. Make sure that the student has mastered that one and understands completely what the entries mean and can rattle off all the products with the numbers 1 to 5 first. Then they have a sense of what the multiplication table is doing and what it actually means, what the entry means. 3 times 4 is 12. The student should have a mental image of what that is. It's a rectangle, a 3 by 4 rectangle, and we're counting cells. That's the primary geometrical understanding that we want the students to have. So we emphasize that by starting with the 5 by 5 table. Then it's reasonable to attempt to learn the 10 by 10 table by doing it in stages and by essentially going through rows, multiples of one given number. Starting, of course, with row number 1, which is very easy. And then the second easiest row is surely the multiples of 10. 10 times 1 is 10, 10 times 2 is 20, as we've already marked. Then the next simplest one are the even numbers, the multiples of 2. So the student can learn multiples of 2. And then after that, multiples of 5 are the next easiest. So one could easily spend a week or 2 weeks on each one of these rows, learning products with 10, learning the products with 2, learning the products with 5, learning them really well, and going back and reviewing the ones that you've already done. After this, I suppose 3 would be natural, then 4, and then 6, 7, 8, and 9. 9 is actually a little bit simpler than some of the other ones, so you could do that one earlier as well. But I think it's especially nice to start with these 4. These are probably the most important ones. Multiples of 2, multiples of 5, multiples of 10. Another point to emphasize is that one should work systematically and thoroughly. So it can take quite a long time for students to learn this table. One shouldn't hurry it. One should go slowly and steadily and make sure that the importance of it is emphasized. The students are learning something important when they're learning this table. They're basically learning a skill that 1,000 years ago only very few people had, and it was a very valued skill. In fact, without the Hindu-Arabic number system, this skill is a very, very difficult one to acquire. And another strategy that I would suggest is to use the squares as an anchor. That big 10 by 10 table can seem a little bit daunting, but if you concentrate on the diagonals as kind of anchoring points, they can be good reference points for nearby ones. So let's just emphasize the squares. Here they are again. 1 by 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. And then we have correspondingly bigger squares. 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, and 10 times 10 is 100. And for something like 7 times 7 equals 49, it's good for the student at some point to actually see a 7 by 7 square and to count them and to check that yes, there are in fact exactly 49 cells in this square. Not 48, not 50, not 73, but exactly 49. So it's not just something that you memorize because someone is telling you. It actually represents a physical reality that you can check. Same with all of them. Okay, so let me again go back to the table and just explain briefly how we can use these as anchoring points to make it easier to get neighboring values in case we've forgotten. All right, so here's our table again. So suppose that the student is asked what's 7 times 8 and they cannot remember. They don't remember that it's 56. Perhaps they remember that 7 times 7 is 49. Okay, so if 7 times 7 is 49, then 7 times 8 is going to be 7 more than that. To go from here to here is adding 7. 7 times 7, 7 times 8. We're adding 7. So then they can say, all right, well, I know that 7 times 7 is 49. If I add 7 to that, then I'm going to get 56. Hopefully they can make that calculation. Or maybe if they want to know what 7 times 6 is, well, then they could possibly subtract 7 from 49 to get 42. So that's why I say these are something like an anchor, that if you remember them, then at least you have a ballpark figure for what the other ones are, and you can get the other ones, at least the ones sort of in this area here, not too far from the diagonal, by adding or subtracting the appropriate number. I want to say a few words about an alternative approach to the multiplication table that has become fashionable in certain circles. In certain schools, students learn the 12 by 12 table instead of the 10 by 10 table. So they go further. They learn also multiples of 11 and multiples of 12. In fact, in my daughter's school, she learned the 12 by 12 multiplication table. Now, in my opinion, this is only my opinion, this is not a good idea. Why not? Well, because our arithmetic is based on the Hindu-Arabic system, and it's a base 10 system. It's based on powers of 10 and using powers of 10 to help us in organizing our arithmetic. So it's important that students understand and get on this track of multiples of 10 being all important. Eventually they learn that after 10, things repeat in some sense. So learning the multiplication table with 11 is a lot like learning the multiplication table with 1. And learning the multiplication table with 12 is a lot like learning the multiplication table with 2. Actually, it's a combination of the table with 2 and the table with 10. It's not necessary or desirable for students to learn the 12 by 12 table. Another reason is simply that 10 times 10 is 100, while 12 times 12 is 144. So there's quite a lot more to learn in the 12 by 12 table. Now I know 11 multiples of 11 are pretty simple, but nevertheless this additional work that's necessary is not really worth it. It's already enough of a burden for students to learn the 10 by 10 table. I would much rather that they learn the 10 by 10 table really well than the 12 by 12 table kind of really well. All right. Simpler is better. And of course, another very, very important point concerns calculators. Yes, calculators can multiply for you. You can press 6 times 7 and the calculator will tell you that it's 42. Do not use a calculator. Primary school students, years K to 6, a calculator is completely unnecessary and even counterproductive. Students in those years should not even see a calculator as far as I'm concerned. You are not doing your young people a service by getting them up to speed with technology, etc., by giving them calculators. By all means, give them iPads to play around with and so on. But when it comes to doing arithmetic, pen and paper, or even better, pencil and paper, are the key tools. Right? That's all what a student needs, and that's the best thing for them. It's so important that they actually get practice over and over and over again, doing multiplications, figuring things out if they haven't memorized it, making work on the page. Very, very important. Learning the multiplication table builds discipline, of course, but it also makes students aware of number patterns. They get to become familiar with numbers in a way that working with calculators doesn't. This prepares the way for algebra later on. So very important, do not do your students or your children a disservice. Take their calculators away from them until they get into high school. Then, yes, calculators have a good and useful role. But when learning arithmetic, avoid them. All right, so that's good. It's a very big topic. Of course, I'm only spending a few videos on this, but in practice, in actual real life, students spend a lot of time and ought to spend a lot of time mastering this very important skill. And hopefully it's a little bit fun. So next time we're going to try to make it a little bit fun by by introducing some tricks and showing you some applications and some problems with multiplications. So some tricks to make multiplication easier. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.